Hello, everyone. In this video, we're going to be going over problem 3.9 in the Fundamentals of Mass and Heat Transfer textbook. Going down to it. So this question poses that the wind chill experienced on a cold, windy day is related to increased heat transfer from exposed human skin to the surrounding atmosphere. Consider a layer of fatty tissue, such as your skin, is about 3 millimeters thick, and the interior temperature is kept at a nice body temperature of 36 degrees Celsius. On a calm day, the convection heat transfer coefficient is about 25 watts per meter squared Kelvin, but if there's a wind speed of 30 kilometers per hour, the convection coefficient reaches about 65 watts per meter squared Kelvin. And in both days, we are to assume that the ambient temperature is negative 15 degrees C. So I've already gone through the problem uh, through its entirety. Over here, there's a brief drawing of just like the skin and the heat transfer going through it. So this problem doesn't give any kind of emissivity for the skin, so I'm just gonna choose to ignore it in this problem. Uh, if you don't want to, you can probably just quickly Google what is the emissivity of skin or fatty tissues usually. But another reason why I just even chose to not deal with any kind of radiation is mainly because because surrounding temperatures are given. It could probably be assumed to negative 15 degrees C, but I just didn't choose to do it in this case. So the first part of the problem asks what is the ratio of heat loss or the heat flux on a calm day versus a windy day. This is can very easily be done just by uh putting the heat flow on a calm day over the heat flow of a windy day. You know, the heat flow due to convection is simply the convection coefficient times cross-sectional area times uh outs times T1 minus T2. In this case, it would be the T skin minus the T ambient. We don't know T skin, but that doesn't matter since the calm and windy days, uh, we are assuming that to be just for the sake of it, we're going to be assuming that the temperature of the skin is equal. So so we are just going to be looking at the ratio of the heat of the convection coefficient. So 25 over 65 is about 0.384615. So the heat transfer on a calm day is 0.384615 of the heat transfer on a windy day. Next up, we are asked what will be the skin outer temperature surface for the calm day and for the windy day. For this, we can just do an energy balance. We are assuming steady state because the problem said that the interior surface is maintained at 36. So we know that the inside of the skin is the same temperature, the outside of the skin is the same temperature, so it is steady state. As I said before, going to be just ignoring radiation for this problem, and uh, the uh, the uh, coefficient of conduction for fatty tissue is about zero point 0.2. I just Googled, searched this value, what it about works. So, you know, conduction, the heat flow due to conduction is equal to Ka over L times Ti minus T skin. And that's going to be equal to the heat flow of conduction on the calm day, which is equal to HA times T skin minus T infinity. plug in some values. You're going to get that since t is an unknown, you need to know what the coefficient times t skin is equal to. So I got a coefficient of 91.6667 for t skin, which is going to be equal to 2,360. So you just divide both sides by 91.66 repeating, and we get a T skin value of about 22.09 degrees Celsius on a calm day. We're going to do this once again on the windy day, except this time the coefficient of convection is going to be equal to 65. Go through all this, and we're going to get a T skin, a temperature of the skin of 10.82 degrees Celsius. Next, for the final part of this problem, we're asked what temperature would the air have to assume on a calm day to produce the same heat rate occurring with the air temperature at negative 15 degrees C on the windy day. So pretty much here, we're now looking at a much lower outside temperature than initially with the calm day coefficient of convection, even though it would probably change if the temperature drastically changed that much, but uh, convection is annoying to figure out. So we're just going to be going through with this. So first thing we're going to do is knowing the values for the windy day, we want to determine what the heat flux is. So we just plug the T skin into the equation for heat flux due to convection, which is just the convection coefficient times the change in temperature, to get 1,678.3 watts per meter squared. I also just did a quick check via conduction to see that with an energy flux such as this, the T skin has to be 10.82 degrees Celsius, which is the temperature, which is the same temperature for the windy day, even if it is a calm day, but still much lower. So now we fill out the equation. In the case of a calm day, figure out what temperature we need to get to this value here. And I got a value of negative 57.132 degrees Celsius. I don't know about anyone who watches this, but that is pretty cold. I would not want to be outside at that temperature. So that's so yeah, that is how that problem is done. And yeah, thank you very much for watching the video. I hoped that this that my explanation would help. And thank you very much.